Okay, continuing on here with some gas law problems. Let's look at what is provided here in the text of the problem, and then let's see how we can apply our equations to it. So we're really looking for there's two different types of problems basically with this approach. Either the problem is giving us enough information to directly use the ideal gas law, or the problem is describing a gas that is present in two different sets of circumstances, where maybe there's some kind of change in one of the variables, the pressure changes or the volume changes. If we have enough information to use the ideal gas law, we can just use the ideal gas law, solve for whatever's missing, maybe adjust units to solve the problem. But if we have the two circumstances, what we're going to do is use the ideal gas law to figure out what the correct equation is that will relate the two sets of circumstances. So let's look at the problem and try to figure out which one it is, which type it is, and then we'll go through trying to figure out what to do. Okay, so we fill a balloon with helium gas to a volume of 2.68 liters at 23 degrees Celsius and 789 millimeters of mercury. That would be the pressure. Then we release the balloon. What would be the volume of helium if the pressure changed to 632 millimeters of mercury? Okay, so there's a change in circumstance. The pressure is different, and we're actually solving for the volume, so the volume is also different, right? But the temperature was unchanged. So let's kind of categorize our variables here. So changed versus unchanged here, because this is part of what we're going to want to do. Pressure changed. Volume is what we're solving for, so the volume apparently is going to change. I suppose we could do a calculation and find out the volume didn't change, but that would be pretty weird, the way these equations are going to be set up. Now, unchanged, we're told the temperature doesn't change, so T is unchanged. It's not directly stated, but this is the same sample of helium before and after you let the balloon go, so the number of moles doesn't change. And of course, R never changes, so R will always be unchanged. Now, if we have this type of problem with two sets of circumstances, what we want to do is start with PV equals nRT, and then put all the changing variables on one side, the unchanging variables on the other side. And in this first example, that is exactly the way we learned the equation. P and V are changing, nRT are all unchanging. And what that means is that N times R times T, since neither of those change from the first set of circumstances to the second set of circumstances, nRT is a constant for this particular problem. So another way of saying that is that PV is equal to a constant, right? And this is the leap that we want to make in evaluating the problem. If P times V always equals the same value, that means the first pressure and volume given in the problem, P1 and V1, will equal the same constant as P2 and V2. And then if we pull out the constant, we have an equation that relates the variables that are described in this equation. P1 times V1 is equal to P2 times V2. That's actually Boyle's law, right? But again, it doesn't do you a lot of good if you memorize that, because you'd still have to figure out that it's appropriate for this problem as opposed to all the other gas laws that we encounter. Now, once we get here, we're asked to solve for the second volume. So I want to solve for V2, so I can just rearrange this equation by dividing through by P2. So V2 would equal P1 times V1 over P2. And from there I can just plug in. So the initial pressure is 789 millimeters of mercury. The initial volume is 2.68 liters. And then the second pressure fell to 632 millimeters of mercury. Now, there's no need to change the atmospheres in this problem, because the way we rearrange the equation, as long as the pressure units are the same here, they're going to cancel out. We're going to be left with just the leftover volume units, right? And since we're solving for V2 here, that's good that we just have those volume units. Now we need our calculator. Let's put it in my bag. So 789 times 2.68 divided by 632. Okay. Okay, and all of our data there is 3 significant figures, so this would be 3.35 liters would be the new volume of that balloon. So as the balloon rose through the atmosphere and the pressure went down, the balloon is going to expand because pressure and volume are inversely related here, right? Since P times V is equal to a constant under these conditions, if P goes up, V has to go down. If P goes down, V has to go up. So they're inversely related. Okay, so we can do that with lots of different gas laws. We'll be able to derive the right equation just by kind of evaluating the way information is provided in the problem without memorizing anything other than PV equals nRT. Okay, let's look at the next example here. So Goodyear Blimps, which fly over sporting events, right? Back when there used to be sporting events, I guess. Although I guess maybe the blimps could still be out there showing the empty stadiums at the moment. Hold approximately 150,000 cubic feet of helium. So there's a volume. It's a kind of different volume unit, but that's V. So that is the volume. If the gas is at 23 degrees Celsius, that's the temperature. And 1 atmosphere, that would be the pressure. Right? What mass of helium is in a blimp? So we're going for mass here, but the important thing to recognize here, V, T, and P, that's 3 of the variables in the ideal gas law, because remember R is not a variable. So we have everything we need here to solve for the remaining variable, which is N. So this question is just going to involve plugging into the ideal gas law. Now, when we do plug in, we will have to be careful with our units. So let's just start with PV equals nRT. And if I want to solve for n, I just need to rearrange that equation. So I'm going to divide both sides by r and t. And that'll leave n alone on one side, and it'll give me PV over RT on the other side. Okay. Now I flip-flopped left and right there too, so just make sure you know what is going on with the little bit of algebra to rearrange that equation. I put n on the left because that's what we're solving for, and I'm more comfortable doing it that way. Okay, now all we have to do is plug in PV, R, and T, but what I'm going to do is I'm going to put R in here first. And R is on the bottom, and we said before R is 0.0821 liter atmospheres per Kelvin mole. Now, for my class at least, I will always give you R on a test. I find that you hopefully practiced enough problems that you'll probably have R memorized. I just don't want somebody to, interpose a couple numbers and get a problem wrong because they just recorded it wrong. So I will provide it on a test. But yeah, if you've practiced enough, you will probably remember it because it does come up in at least half the problems. Now, the important thing about R here is I need to match the units on R when I put in all the other variables. So if I go to put my temperature in here on the bottom, it's got to be in Kelvin. So 23 degrees Celsius, I add 273 to that, and that would be 296 Kelvin. So my temperature here is 296 Kelvin. So that's just 273, not times, plus the 23. Right? So double check that to get it is 296. The pressure that goes in the top should be in atmospheres, just like the pressure unit that is in the gas constant. So 1 atmosphere is fine there, the way it's given. But the volume here is the other one that we're going to have to change, because our volume should go in terms of liters. So I want to take, maybe over on this, let me do it down here at the bottom so I don't get in the way of finishing the gas law calculation. 150,000 cubic feet, and we're given here at the end of the problem the relationship between liters and cubic feet. There are 28.3 liters in 1 cubic foot, and that will give me, my L got a little C look in there, and it looks like my pen is about to run out, so let me switch, see if my other pen is, nope, that one is a little bit funky. We'll go to the blue pen. 150,000 times 28.3. Okay, and that's 4,245,000 liters. Now, We really are limited to 2 sig figs here in this problem, right, from that initial volume, also from that temperature and that pressure, but I don't want to round yet, so I'm going to keep that whole set of numbers. 245,000 liters. Now, if I multiply out here, a lot of my units are going to cancel. Atmospheres is going to cancel, liters is going to cancel, kelvins is going to cancel. Now, what we have here are stacked fractions with the fractional units on R. Moles is on the bottom of the fraction that's on the bottom of the bigger fraction. That means in the end it's back on top of the unit. So this will tell us how many moles of our sample there are. So if I'm 1 times 4,245,000 divided by 0.0821, right? And then the 296 is also on the bottom of that fraction, so divided by 296. And I did something wrong because I got to the negative 11th, so let me try that again. 4245000 divided by 0.0821 divided by 296. That makes a little more sense. So that is 174,680. And I did round a little bit there, but I think that is okay in terms of how much I'm rounding. I'm not going to change my answer much since I'm going to 2 significant figures at the end. Now, we're told this is helium, so that's moles of helium, but we're actually asked for mass in the problem. So we actually want one more step here, and that's to take our answer, moles, and convert it to mass. So we go to the periodic table, and we can find out what 1 mole of helium weighs. And 1 mole of helium, where did my periodic table get to? Okay, well, we're getting toward the end of how long I can make this video. So I'm pretty sure it's 4 grams of helium. So let's just use 4.00. It maybe is slightly different. But multiply by 4 there. Right, and now this answer we want to make sure is just 2 significant figures. So it is 698,000, right? But I'm going to round that to 2 significant figures, so that would be 7.0 times 10 to the 5th grams of helium. Right? And we were just asked for mass, so that is a reasonable answer. It might be a little better to convert that to kilograms, right, which would be about 700 kilograms, right? Now it is a 2 significant figure, 700, so 7.0 times 10 to the 2nd power kilograms of helium. Okay, so a little more straightforward there, just plugging into PV equals nRT. We do have to be wary of units though. We get the right units to cancel out with R, right? And then possibly what we're solving for is not one of the units that's in the ideal gas law, but we know some things about how to change from certain units to other units so we can get to mass with the molar mass. Okay, we'll come back for the next page and a few more practice problems.